So you can kind of see what is happening in terms of the setup within all of this, and understand that we can do this at any speed. Some very, very slow speeds. We did 6 degrees per second in there. You could go down to 30, 20, even 10 degrees per second, all the way up to probably up to close to 600 degrees per second if you wanted to get into very, very rapid, almost kind of neurological, or getting close to stretch shortening cycle based activities. So now what we need to consider is the kind of the methodological issues and concerns we have with isokinetics. So what are the primary considerations? And we'll deal with these kind of in sequential order. The first one is the notion of participant positioning. Remember that what we're doing when we're using the dynamometer is we are isolating the joint or the segment that we want to work on. Now that means fundamentally that the segment we want to work on has to be fastened to what is called the input arm. And the input arm is the section on the dynamometer to which the limb is being connected. So in this example here, this is the input arm here, and this is kind of an extension of the dynamometer. This is the main dynamometer unit here. This is the input arm. So what you can see is that we'll talk about limb alignment in a moment, but you can see that this strap is over the main muscles that are involved in the action. We've also got to ensure that we get the positioning of our participant correct in relation to the way in which that they are lined up with the dynamometer itself. And the reason being, we don't want to get injury. If we don't have the participant correctly positioned and secured, we're going to end up with potentially misalignment, which we'll talk about now. Alignment is, remember that you are isolating this segment. You're isolating, let's say, the prime movers of the knee, the quads and the hamstrings. So we're dealing, therefore, with the amount of torque going through those muscle groups to change the range of motion around the knee. So fundamentally, the knee, in that example, has to be lined up with the axis of rotation around the dynamometer. So if we look at the video here, there is the center point of the dynamometer itself. So you've got to imagine that there is a rod passing through the knee joint, and it has to line up both horizontally and vertically with this axis of rotation around the dynamometer input arm here. Because you can see that fundamentally the participant is fully connected to this now. This is an extension of their lower limb. It's an extension really of the knee and the tibia and the fibula, because we've secured, in this case here, we've secured the ankle. It's connected with these strapping. So if we misalign the participant against the axis of rotation around the dynamometer, so imagine that the participant was skewed and was sitting out of line. We've got them rotated more going clockwise on the chair here. What would be happening is the forces that are going through the knee are misaligned to the direction at which this dynamometer arm is pulling. And remember that fundamentally, once the test starts, the dynamometer arm is going to move. All that changes is the rate at which it moves, depending upon how much force you apply. So if that happens, we're likely to then start putting forces through the knee joint which are out of line with its own axis of rotation. So alignment becomes really important. You have to remember that that input arm in the whole of the dynamometer is absolutely an extension now of the joint in which you're working with. And to achieve that, it is not just simply lining the participant up in terms of just, oh, well, I'll just look at the knee here. There's so many things that we can do. We can change the way this whole dynamometer section here rotates. We can change the height of this dynamometer section here. The chair itself is on a rotational system, so the whole chair can be spun. The chair can move what we call fore and aft, so we can slide. You can see here this little handle over to the left here. This section here can move the participant forward, but this whole chair section here can slide backwards and forwards. So I can move the positioning of the knee joint in this example in a horizontal plane in alignment, or trying to get alignment with this axis of rotation here. You've also got what's called a monorail. So the chair sits on a monorail and slides in this plane like this along this rail, allowing me to bring the participant closer or further away from the dynamometer itself. So it's quite complicated, and there's a lot of fiddling around to undergo in terms of ensuring we've got appropriate axis of rotational alignment. The next thing we have to consider is the range of motion. Now remember that what's happening is you're trying to assess the amount of torque being produced while the limb is going through, in this case, a state of, say, from flexion to extension and back. So we need to know what the range of motion is of that participant for that joint, and that fundamentally limits sets the limits over which the joint and the muscle groups are going to be activated, and we have to do that, and it has to be controlled. And so what we have to know is, are they able to get to what we call the constant phase? The constant phase is the phase where they actually are no longer accelerating or no longer decelerating. They're actually working at the target angular velocity. So the only way we can do that is by allowing the participant to calibrate with you, the practitioner, their range of motion over which the joint is going to operate. So we need to know that, because we need to understand the length tension relationship of the muscle. So we need to establish what the full range of motion of the joint is. And you need to do that a couple of times, because the first time they do it, they may be a little unsure what's required. So they need to do that multiple times to establish that optimal range of motion. And I'll show you about how you prevent overshoots with that. And then the final thing to think a little bit about methodologically is the number of trials. Well, what's the minimum? Well, the minimum of trials is 3 per each angular velocity. So you would need to make a decision about which angular velocities do you want to work at. You need to make a consideration about what muscle action you want to work out. Is it eccentric? Is it concentric, for example? What is actually recommended by Mike Gleason, who wrote a very good review paper, it's quite old now, but a very good review paper in sports medicine, is that you do 5 trials and we only count 3. So what we do is we discard the first repetition and we discard the 5th repetition. The reason that we do discard the first is almost like familiarization, and generally what happens by the time we get to the 5th, they were starting to be fatigued. So we tend to take the middle 3 trials and then we average across those middle 3 trials if we're looking for kind of our peak torques and our average torque values. Now, let's think about this in terms of the alignment. So we can see our participant here, and you'll see them do multiple repetitions. And just have a little think about what we're seeing when we think about the methodological considerations. So you can see that the dynamometer input arm is moving absolutely in sequence with the limb that's been isolated. There is alignment through the joint, bearing in mind that there will be obviously some movement here across the knee, and you have to achieve this by palpating the muscles to make sure that you can locate the bony landmarks. We have the dynamometer set up so her rotation means that we're not too internally or externally rotated. The dynamometer height is set accordingly so that we've got horizontal and vertical alignment through the knee joint. And we've ensured that we've got them close enough to the dynamometer, close enough and also far enough away, it's perfect alignment, so that we're not causing, again, an internal or external misalignment of the knee against the center point of the dynamometer, which is this point here. And if you look on the screen now, you can see the traces for both the extensors and the flexors of the knee. So if you watch now, we're going from flexion to extension, and you can see the way the trace is changing on the screen over the range of motion. If you watch now, she's coming up into full extension. We're now going to go into flexion, and you'll see the flexion trace starts to develop. So we're now able to isolate the extensors and the flexors of the knee. Okay, so let's have a little think about what is going on in terms of the alignment and why this is an issue. So in this example here, we can see what happens when we do, in this case, it's knee flexion to knee extension. So what we've got here is we've got our kind of our femur, and we've got our quads, and we've got our hamstrings, and you can see down here the tibia and fibula. This is the dynamometer here, and this is kind of the device you're pushing against. What you've got to remember is when we're doing this, there is an external force that is acting on the limb, and of course that is the force of gravity. So what is happening is when we are going through our range of motion, when we're going from, say, flexion to extension, we're working against gravity, and when we go from extension to flexion, gravity is working and is actually trying to accelerate the limb. And it's really important, we'll talk about this later on in this session, that we actually do what's called a gravity-based correction. In here, you can see the muscle force that's being produced, and this kind of the torque, and of course you can see kind of where that angle is in terms of the force at this moment in this movement that we are seeing here. So in the example that we've got here, what we can see is the way in which the forces change as we move through our range of motion, and we can start to see particularly where the gravitational forces change. Remember that fundamentally gravity is always acting on the joint and on the limb, but actually you can see that as we move through our range of motion, can you see that the gravitational forces change as we go through that range of motion? So you can see this kind of changes at different points as the limb moves throughout its kind of range of motion. You can also see on here what is happening in terms of the lever arm. So this is kind of these D values here, the DAs and the DBs, and it's understanding, I mean, it's, you know, that fundamentally as the limb is moving, there has to be some displacement around the joint. So we have to take that into account, and that is why fundamentally taking particularly the role of gravity into account is fundamentally important. If we don't gravity correct, then we don't know how much of an effect gravity is having, particularly when the limb is accelerating up to the isokinetic speed that we want, and when it is that's say in extension, and when it's accelerating going into flexion in this example, and gravity is trying to increase that acceleration. When we're going from flexion to extension, it's acting almost like a braking force. When we're going from extension to flexion, it's acting like an accelerational force. So we need to take gravity and its role into account. On these examples here, what we can see is what happens when we misalign the axis of the rotation. In the panel to the left, you can see what happens is, here's the input arm, so here's the dynamometer, and this is the input arm here. Here's the center of rotation around the knee. And so what you start to see is that the forces start to change in terms of where the force is actually occurring across the joint. We want to evaluate really the forces that are being used in terms of our prime movers, but actually what we start to understand is if we misalign, in this case it's an extreme misalignment, although yes the prime movers are being engaged, the force is actually acting in the lower limb. It's actually acting across the tibia and the fibula, and you're likely to cause quite significant injury if you have this misalignment, particularly at high angular velocities. In this example here, it's poor parallel alignment, and what starts to happen is if we get poor parallel alignment, we start to get rotational forces on the limb. So this is basically where we've either got the knee either internally or externally malaligned in terms of rotation against the dynamometer input arm. So if you imagine that the knee is inverted by 10 degrees, so we've got an internal rotation of 10 degrees beyond what it perhaps should be against the dynamometer arm, which is working in its correct axis of rotation. So now what's happening is we're getting rotational forces, in this case again across the tibia and fibula. So we're not really getting accurate readings in terms of the forces, or the torque I should say really, but the torque being enabled to produce the change in muscle action around the knee, and we're causing these rotational forces in the tibia and fibula, which are likely or potentially likely to result in adverse issues such as injury. So alignment becomes so fundamentally important in terms of getting valid, and of course consequently if we misalign differently each time, reliable results. So there are some additional method-based considerations. Well, we've touched on one of these already, which is gravitational correction. But the other one is what's called the angular velocity compensation. So during isokinetic testing, the angular velocity of the input arm and the segment increases from a stationary position, so an angular velocity of 0 degrees per second at the start of the movement, to the preset target value. So you remember that we showed earlier on in this session that, let's say we want to work at 120 degrees per second, we start at 0, so if we're working concentrically, you're going to try and accelerate the limb, and you're going to try, and of course it will be easy initially, and then suddenly the dynamometer will apply a resistance to slow you down, so you're no longer working or you're no longer accelerating, and it will keep adjusting that throughout the range of movement. So understanding this is important. We have to take this into account, because there is always an acceleration phase followed by what we call the constant angular velocity phase, where angular acceleration equals 0. And then you get a deceleration phase, falling back to 0 at the end of the range of motion. So we go through kind of an acceleration, constant, and then we go through a deceleration. Now, why is that important? It's important because what we can see on our panels here. If you look to the panel to the left, on this here we've got our time in seconds, and then we've got our moment in Newton meters, that torque or moment, however you want to describe it. And what you've then got is the secondary y-axis shows us our angular velocity. So in this example here, the angular velocity that we're asking the participant to work at is 300 degrees per second. They've referred to it here as rads, but it's 300 degrees per second. So what happens is, look at the angular velocity. Notice that it starts at 0, and then we're going through this time period. This is one movement, so it's through the range of motion. We accelerate, we then get to the constant phase, and then we start to decelerate. And now what you can see is the corresponding torque, or the moments as they're referring to it here, it's the same thing, throughout this range of motion. So why is that important? Well, it's important because what you can see on the panel to the right, the only period where we're actually working isokinetically, that is where we have got a constant angular velocity, is this med section here, where fundamentally we're at 300 degrees per second, or as they required here, it's 5.5 rads per second. That means that it's only during this period here that we can actually calculate the torque that's being produced. So for example, this would be the peak torque here, and then we would take the average torque across this range. No other phase are we actually getting isokinetic assessments. That's really important to understand. Although we can assess across the range of motion, and absolutely you can do that and assess across the range of motion, fundamentally the only area where we're getting the absolute most valid data is the section where the angular velocity has 0 acceleration. It's constant. We're accelerating, we're decelerating. The net result is that we haven't got the isokinetic phase, we therefore haven't got valid data in here or in here. The second thing, which we've already referred to, is the notion of gravity correction. So as we've written here, if you've got movements in the vertical plane, so for example knee extension, knee flexion, the forces acting on the limb lever system are the muscular force and gravitational force, and the latter is generated by the mass of the limb and the lever arm. So we need to take into account how much of effect gravity is going to have, and we do that by weighing the limb. So we would weigh the limb. Once we know the weight of the limb, we can then calculate the acceleration due to gravity on that load, because force equals mass times acceleration.